So now that we know how to find the point estimate of a population mean, the sample mean, the next step in the inferential process is to go about constructing a confidence interval about that particular point estimate. The interval of numbers that we want to construct is going to be of the form point estimate plus or minus margin of error, just like it was when we were doing the confidence intervals for a population proportion. Remember, for the population proportion, we went p hat plus or minus z sub alpha over 2 times the square root of p hat 1 minus p hat over n. The z sub alpha over 2 we referred to as the critical value, and the square root of p hat 1 minus p hat over n is the standard deviation of p hat, or the standard error. The reason that we use a critical value of z is because of the fact that the distribution of p hat is approximately normal, provided n times p hat times 1 minus p hat is at least 10. And so, using the logic that we introduced for the confidence interval for a population proportion, I have on the screen here what would be a reasonable method for constructing a confidence interval for a population mean. X bar is the point estimate, plus or minus z sub alpha over 2, the critical value, times the standard error of x bar, sigma over the square root of n. This method will work provided that x bar is approximately normal. Remember, when is x bar approximately normal? There are two circumstances under which x bar will be approximately normal. Right, so x bar will be normal if the population itself is normal, or
if the sample is greater than 10.
Yeah, if you have a large sample size, then the distribution of x bar will also be approximately normal. In order to construct the interval that's circled in blue, however, we're assuming that we know sigma, the population standard deviation. It doesn't seem real reasonable to say that I know sigma, but I don't know mu, the population mean, right? After all, if you think about this for a sec, sigma is found by taking the square root of the sum of x minus mu quantity squared over n. So how could you know sigma without knowing mu? Well, the solution to that particular problem of not knowing sigma as well would be to use the next best thing. Use an estimate of sigma. What do you think would be a good estimate of sigma, the population standard deviation? Yeah, use the sample standard deviation, S. So let's go ahead and put S into our formula, and we get x bar plus or minus z sub alpha over 2 times S over the square root of n. That seems good, doesn't it? And in fact, this approach, marked with the letter number 1 there, that approach is the approach that was used for quite some time. It was used for a long time until a guy named William Gossett came along and realized that using z for a critical value when you don't know sigma ends up with intervals that capture the unknown parameter at a lesser rate than you would have thought. Right, so if you were constructing a 95% confidence interval, remember you would expect about 95% of your intervals to capture the unknown parameter. This guy William Gossett found out that using z in that formula 1 actually results in capture rates lower than what you would have expected. William Gossett was an interesting character. William Gossett worked at the Guinness Brewery Company back in the early 1900s. He was a chemist. Okay? And so knowing that that problem exists really bothered him, and so he would work at night on trying to come up with a solution that allowed him to construct confidence intervals that captured at the rate he would have expected. And he was able to figure that out because his chemical theory wasn't jiving with what he was actually observing. Okay? And so again, Gossett spent tons of time at night trying to come up with a solution. He learned that x bar minus mu divided by s over the square root of n, in other words, putting s in place of sigma, does not follow a normal distribution with mean 0 and standard deviation 1. And so what we're going to do now is go off and do some of the types of works that Gossett did. We're going to use a computer and simulation to do it. Gossett did all of this work that I'm about to show you by hand at night for fun.
Bless it.
Right. I'm just going to open a new StatCrunch spreadsheet, and to illustrate this idea, let's just use a normal set of data, and let's just use IQ data. IQ data is approximately normal with a mean of 100 and a standard deviation of 15. Okay? What I'm going to do is randomly generate a bunch of random samples of size, let's say 9, from this normal population where the mean is 100 and the standard deviation is 15. StatCrunch allows me to do this. I can go to Data, Simulate, Normal. I'm going to generate 1,000 rows of data with 9 columns. Again, the mean is 100, the standard deviation is 15. I'm going to leave it split across columns. So basically I'm going to have 1,000 rows with 9 columns of data. Each row will then represent one of my samples. And just to keep this clean, I'll round this data to the nearest whole number so it looks more like IQ data would be reported. So when I click compute, I get the results. And so what I want you to imagine is we went out into this population, okay? And my first row represents the results of my first survey. The first individual I surveyed had an IQ of 110. The next individual that I surveyed had an IQ of 70. The next an IQ of 75, 95, so on and so forth. Then I did this a second time. Went out and surveyed 9 individuals and asked them their IQ scores, and the highlighted row represents their IQ scores for the second time that I did this. A third time that I did this, I got these IQ scores, and so on. And if you scroll down, there's actually 1,000 rows of data in this table for 1,000 different random samples of size 9. Okay? Now, for each of these rows, I'm going to compute the sample mean and the sample standard deviation. To do that, I go to Stat, Summary Stats, Rows. I highlight my columns 1 through 9, and I want to know the mean, and I want to know the standard deviation. And I want to store this in the data table. And then I click Compute. And so you can tell this is the X bar that you would normally get when we, like when we did it in section 8.1 and we're generating random samples from a normal population and computing the sample mean to see how the sample mean varies from sample to sample, right? So here you can see the sample mean was 99.9, my next sample mean 102.1, 101.2, so on and so forth. There's some variability in the sample means. And I'll just, to make this easy, I'll call this X bar. And then this column here represents the standard deviation. I'll call it S for each of the samples, right? So like my first row, my first random sample had a sample standard deviation of 19.5. In other words, that particular sample had a little bit more variability in it than the variability that exists in the population. Because the sample standard deviation is 19.5, the population standard deviation is 15. But you can see that my second sample had a little bit less variability associated with it. You follow? Now, if you go back to these, if we go back to our notes, I'm going to compute two different values now in that data table. The first one I'm going to compute is Z value. Remember, we reserve Z for standard normal, meaning normal with mean 0, standard deviation 1. You can find a Z value by taking the value of a statistic, subtracting the mean, and dividing by the standard deviation of that statistic. Remember that? And so what I'm going to do here is put in specific values because I know what they are, right? My statistic is X bar. The mean of X bar is 100 because that's the mean of the population from which I sampled. The standard deviation of X bar is the standard deviation of the population over the square root of the sample size. So I'm going to compute a column that's X bar minus 100 divided by 15 over the square root of 9 is 15 over 3, which is 5. I'm also going to compute a column that I'm going to call T, because William Gossett called his distribution the T distribution. T is computed as X bar minus the mean, which is 100 as well. But instead of knowing sigma, we're going to pretend that we don't know sigma because that's reality. And so I'm going to use the S that I computed over the square root of the sample size. So if you look, the only difference between Z and T is with Z, I'm assuming I know sigma, and with T, I'm assuming that I don't know sigma, right? And if you look here, we're trying to construct a confidence interval where we don't know sigma. And the original way it was done was simply to use this critical Z even though you don't know sigma. And Gossett found a flaw in doing that. We're going to expose the flaw with this little analysis that we're about to do. Okay, so this column var 12 is going to be the Z column, and then column var 13 will be the T column. I have to create those with StatCrunch, so I'm going to compute an expression in StatCrunch. So remember, the expression that I want to compute, I'll just build it, is parenthesis X bar, right, minus 100, and then divided by 5, right? That was what Z was. X bar minus 100 divided by 5. Click OK, click compute, and these are all the Z values. So I'm just going to put Z in place of what's there right now. Okay? var 13 is going to get T. Same thought. Data, compute, expression, build the expression, put a parenthesis in there. I want X bar minus the mean, which is 100, and then divided by, now this time I'm going to go S divided by the square root of 9. So it's S divided by, the square root of 9 is 3. So it's S divided by 3.
So do you have, so up there, is that X bar, parentheses, X bar minus 100?
Yes.
In parentheses, okay.
In parentheses, divided by S over the square root of 3. Just so you know, you're not going to have to reproduce this on a test or anything like that. This is, yeah, I mean, this is, this is just I'm trying to motivate why we can't use Z in that confidence interval, right? And help you to appreciate what Gossett had to go through.
Yeah, we appreciate it.
Right? Because, you know, this all had to be done by hand back in the early 1900s. So if you can imagine that. So this column is now T. Okay? What I'm going to do is draw histograms of Z and T next to each other so that we can compare the two. and see what they look like. Remember, Z is going to be a normal random variable with a mean of 0 and a standard deviation of 1, right? Because all I did when I computed Z was a simple transformation. Subtracting a value and dividing by a value is not going to change the shape, overall shape of that variable. So x bar is still going to follow the same shape. All I'm doing is centering it at 0 and making the standard deviation 1 by doing this. So here we go. Let's have a look-see. I'm going to draw a graph. And the graph I'm going to draw is a histogram. And I'm going to draw a histogram of Z and a separate histogram of T. Well, here, you know what I'll do? I'll just do them one at a time so I can set them side by side rather than in the same screen. Okay. I also am going to make sure that I set this up so that both graphs look similar to each other. So I'm going to bin this so that each graph starts at -5 with a class width of 0.25. And so this is going to be the histogram of Z. So there it is. And you can see that virtually all the data lie between -3 and 3 and has approximately a bell shape to it. And you would expect all the data to lie between -3 and 3 because this is a standard normal, mean 0, standard deviation 1. Remember, by the empirical rule, approximately 99.7% of the data should lie within 3 standard deviations of the mean, and that's what I'm seeing here. Now I'm going to go graph, histogram, of T. Hopefully these bins are good enough. So again, bin of starts at -5 with a width of 0.25, and I'm going to call this the histogram of T. Okay, now as you compare these two histograms, what do you notice about, first of all, what are some similarities between the two?
The shape is not all that far.
Yeah, they're both kind of, they're symmetric and kind of bell-shaped, right? Where are they both centered at? Both centered at 0, so on average, when you subtract 100 from the mean, you're going to still be at, you're going to be at 0, right? Because that's the mean of the parent population. What's a big difference between the two?
Outliers. Well, if you
Well, one is skewed to the right more so than the other, looks like.
Well, if you just focus on these, right? You don't have any values that are less than -4 for the Z, right? And you don't have any values bigger than probably even 3 over here, right? The biggest value we saw was less than 3, whereas you have values even bigger than 4 over with T, right? And so T has more variability in it. It's more dispersed than Z is. That additional dispersion that you're seeing in T is solely due to the fact that you did not know sigma. Because the only difference between Z and T is that in T I had to use S, the sample standard deviation, whereas in T I used a constant, 15, the population standard deviation. So the only difference between Z and T is because I didn't know sigma with T, and by not knowing sigma, you can see that there's additional variability in that value, x bar minus mu divided by a standard error. So this additional variability is what accounted for the fact that Gossett's capture rate was off. By not knowing sigma, you introduce additional unknowns in the construction of the confidence interval. And so that's, again, and Gossett did that for many, many, many different sample sizes. right? And so Gossett learned that when you don't know sigma, you can't use Z. And so he came up with his own sampling distribution. And his sampling distribution was called student's T distribution. And you should be saying to yourself, shoot, I thought the guy's name was Gossett. Why is he saying student's T distribution? If I came up with my own distribution, I would sure as heck call it Sullivan's distribution, right? So Gossett was using data that he obtained from his work at the Guinness Brewery, and Guinness in general is very secretive about their brewing process, and so they allowed him to publish his results, but he had to publish it under a pen name, and the pen name that he chose was student. Okay? And so we just went through this activity with n is 9, like I talked about. Then the next thing we're going to do is I'm going to repeat this process for a sample of size 16. And I'm going to go really quick over this one. So remember I said I'm going to do a sample of size 16. So data, simulate, normal, 1,000 rows, but this time 16 columns corresponding to my sample size 16, a mean of 100, a standard deviation of 15.
Rows.
Oops, 1,000 rows. Split across columns. We'll round to 0 decimal places. Click compute, and there's our each sample of size 16. For each sample, remember what I did is I computed a row mean and a row standard deviation. And I store that in the data table. So the row mean we call X bar, the row standard deviation is S. For each of the samples, we're going to compute Z and we're going to compute T. Data, compute, expression, build, parenthesis, X bar minus the mean of 100 divided by 15 over the square root of 16, so 15 over 4. That's Z. Compute. There's Z. Now I'm going to compute T. Data, compute, expression, build the expression. X bar minus the mean of 100 divided by S over the square root of 16, which is 4. Okay. Compute. There's T, graph, a histogram of Z. Let's just see what it looks like. There it is, right? So let me title that, I forgot to. Histogram of Z. Start at -5 with a class width of 0.25, just so that we're consistent. There it is. You can see sometimes you're going to end up with these weirdos, right? He's more than 3 standard deviations away, but that should happen, just not very often. Right? Graph, histogram of T, -5, 0.25. Histogram of T, compute. What do you notice? They're very similar. I would argue that T still has a little bit more dispersion than Z, but this T distribution certainly has less dispersion than the T distribution did for sample size of 9, right? that shouldn't be super surprising to you because you all know the law of large numbers, which tells you that as your sample size increases or the number of trials increases, there's less likelihood of wandering from one's goal. So in other words, for a sample of size 16, odds are that sample standard deviation is closer to the true population standard deviation, and therefore T is going to be closer to Z, right? Using fancy schmancy language, students' T distribution is asymptotically normal. As your sample size n increases, even though you don't know sigma, students' T distribution is going to start acting more and more like the normal distribution, is the moral of the story there. But it sounds cool to say asymptotically normal, doesn't it? So what I'm hoping is that, and like I said, we did this for samples of size 9 and samples of size 16. Historically, these student T distribution tables have gone from samples of size, say, 2 up to samples of size 30. Because historically, after you got to a sample of size 30, the difference between the T distribution and the Z distribution wasn't enough to justify using the table. And so, historically, when samples exceeded 30, this distribution right here, this model right here, was used for constructing confidence intervals. In other words, you could use the normal critical value for samples of size 30 or more, right? But for samples of size less than 30, you would use students' T distribution. Again, you now know that's because students' T distribution is asymptotically normal, okay? So I'm hopeful now that these properties that I'm about to share with you are going to feel reasonable based on our little simulation. Number one, the T distribution is different for different degrees of freedom. Isn't that pretty clear from the 2 graphs that we created? Right? This student's T distribution with sample size 16 was different than it was for a sample of size 9. And oh, by the way, what the heck is this degrees of freedom that you're talking about? We first introduced you to degrees of freedom back in section 3.2 when we found the sample standard deviation and we were dividing by n minus 1. Remember that? We said we divide by n minus 1 because we were using x bar in place of mu in the construction of the standard deviation. And because we used an estimator, we lose a degree of freedom. That's what this is about as well, right? So for construction of confidence intervals for a mean, the degrees of freedom is always the sample size minus 1, right? And so here, for a sample size 16, our degrees of freedom would be 15. For a sample size 9, our degrees of freedom would be 8. And we can see that as the degrees of freedom goes up, the distribution of T behaves more and more like the standard normal. T distribution is centered at 0 and symmetric. We can see that. Because it's a density curve, the area under the curve has to be equal to 1. Because of the symmetry, the area to the left of 0 is going to be the same as the area to the right of 0 is going to be 1/2. As T increases or decreases without bound, the graph approaches but never equals 0. Right? So it's asymptotic to the horizontal axis as well. The area in the tails of the T distribution is a little greater than the area in the tails of the standard normal. Why? Because we're using S in place of sigma, thereby introducing additional variability, right? You can really see that here in the histogram for T when n is 9. We have more area in the tails of these distributions over here, right? There's more area here than there is in this standard normal. So the T distribution accounts for that. As the sample size n increases, the density curve gets closer and closer to the standard normal. Again, that's because of the law of large numbers. And so here's a graph that kind of illustrates how the t-distribution in theory matches up with the normal. The normal curve is the one that's in blue. And so you can see in the tails of the distribution, the normal curve is at the bottom, meaning less area as you're further away from 0. The yellow curve is students' t-distribution with n is 5. It has the most area in the tails because there's more variability associated with a sample size 5 than there is with a sample size, say, 15. And so that's why the magenta one is in the middle for a sample size 15. So as your sample size n increases, students' t acts more like the standard normal.